All right, let's get started. I hope you guys had a chance to watch the video for 9.1. It was put up Friday. I think the internet was down on campus Thursday, and since like everything is on StackCrunch from this point on, I can't show you how to do it. So thankfully there was a video from a previous semester, so we can kind of stay on schedule. A quick recap of what we had in it, not necessarily how it works, but what we're doing. Chapter 9 is on, we start doing inferential statistics. This is where we start, and chapter 9 is on confidence intervals. And what it boiled down to was whatever our data, our experiment yields. Or experiment yields, whether it's a proportion. Proportion or mean. Or other things, it's unlikely to be exactly same as the population. But most samples should get relatively close. Assuming appropriate steps were taken for randomness and stuff. It is possible, although highly improbable, for a sample group to have enough outliers from the population that the summary stat, whether it's proportion or mean or etc. To be too far removed from the actual value. Of the population value. That's kind of the reasoning of it. I mean, we could poll people on intelligence. And we should get an average IQ if we were doing IQ. But it is quite possible, although, unlikely as hell. To just get a whole bunch of fucking genius people from different targets and fucking. You know what I mean? Just survey random people and you get a bunch of fucking geniuses walking around. And it's enough to skew the results. It happens then. It doesn't happen often, but it happens enough that statistics isn't an exact science. We can only get close. And we can take steps to make sure we're as close as possible. And 9.1 focused on doing this on proportions. where confidence interval. Or CI, since we say it enough. Is a range of numbers around our experimental numbers. Or around our experimental result. That is likely to include the population value. We give it a percentage, but it is not a probability. But it is not probability. The range of numbers. Either has it. So 100%. Or it doesn't. 0%. The CI percentage, what it does do is it reflects the percentage of other sample groups if conducted the same way. That would include our value. And if you have like a whole bunch of sample groups and they're all likely to include our value, there's a good chance the populations includes our value as well. In its range. And hopefully you have watched it already, but if you haven't, watched the 9.1 video. And you can watch like an applet, we've done, I did different things showing how that's generated. And showing a bunch of sample groups having the same kind of thing. But like the sense, these paragraphs kind of wrap it up. It's not a guarantee that we have the population's results in our range. But it does reflect a high level of likelihood, if our confidence interval is high. And what we had in 9.1, the stat crunch was, we had a couple options. It was, in all options, it was stats, then proportion stats. And then we had some options from here. One sample. Or two samples. And within these, they had data or summary. As today's stuff on mean will have. You also have the option for power or power sample size. And within it was how to finding a sample size that will yield a good result. It had some criteria to be met. We had, and this was same from the chapter 8 criteria. Shit we did in the previous chapter. N times P times 1 minus P had to be greater than or equal to 10. And N has to be less than 5% of the population size. When you do it, mu of P hat, or mu of P is P hat. Which was X over N from the data collected. And standard deviation for P was P hat 1 minus P hat over N, and then you take the square root. That's a summary of what you'll see in 9.1 if you haven't watched it. But again, I recommend watching it if you haven't. 9.2 is today's stuff. 9.2 is on estimating a population mean. 9.1, we estimated a population proportion. Here we're doing a population mean. And if you look back at the chapter 8 criteria under for this stuff. Still applies here. I think my red pen's dying. I might have to grab another. Mu of X, the population mean was equal to the sample mean. And standard deviation for the population, or the standard deviation from the sample is standard deviation of population over square root of N. I do have a dead pen. Now, this poses a problem. This is completely acceptable. Completely normal. Acceptable. But standard deviation throws a monkey wrench into the mix. Throws a wrench into the gears. Calculate standard deviation. We need the standard deviation for the population. But if we had that. I can guarantee you we have the mean already. There's no way to get the standard deviation of the population without having collected all the data, and then you can just take the fucking mean and find it. So like, this is dependent on information we don't have. So enter stage left, my favorite story in almost all of mathematics. Give you a little rundown. There's this dude, his name is Gossett. Gossett works for Guinness Brewery. He's making booze. He's trying to do statistics there. Back in the 1900s with no information. So he conducts extensive research. Extensive, i.e. a shitload of research. And develops a distribution that will work. It actually works. You can start with sample data and appropriately predict information about the population most of the time. You'd be surprised how many people that are mathematicians who like to do math like to fucking drink. It seems like an abnormal percentage. Maybe it's the complex shit we deal with, and it's just nice to let the brain fucking go rot for a little while and think about some other shit. I don't know. His boss won't let him produce the stuff under his name because it's got their business related to it. He can't produce under his name, so he produces under the name student. Not produce, publish. He can't publish under his own name because his boss is a douche. Because of his boss, so he goes by the pseudonym student. So what we get is students' T distribution. You know how we were converting shit to like a normal score, a z-score? This is like a z-score. But it's a t-score. I don't even know if they say t-score. But it's calculated very similar to z. Z was x minus mu, or x bar minus mu over sigma. But we don't have sigma. T is x bar minus mu over S divided by the square root of n. And that's stuff we have from the sample. S is the standard deviation sample. As a reminder, and x bar mu and n we have used repeatedly. I hope you know it by now. If Jurassic Park was filmed back then, he would definitely get the Clever Girl Award. This was some fucking outside the box thinking. And he did it while making fucking ale. That's fucking slick. That's why I like this story. So, it has a lot in common with Z squared. Or the normal distribution. It is, okay, it's symmetric and bell shaped. And centered at mu equals 0. Just like our normal distribution. The area to the left of the center equals area to right, which is 50%. That's also like normal distribution. I wrote A twice. That's funny because he worked at a brewery and I'm over here using AA. See if I have a good. I think I do. Let's see. I might have to download it again. I get it downloading while you guys are doing this real quick. It's got a nice picture. Also like the Z's distribution, the tails approach but never touch the axis. Or 0. There's always some probability, even if it's less likely than being struck by lightning if you go far enough down that tail, there's still something there. Motherfucker, I scrolled down to where I wanted to be. And as soon as I hit enable editing, it took me right back to the fucking top. Let's go take a look at a picture of the T distribution. And then from there, I'll point out the differences between that and Z. So a normal distribution. God, I made that too tall. There we go, that looks good. Well, that's harder to see, fuck it. The blue one is the normal, it's a little bit taller in the center, a little bit, a tiny bit. Notice as we get over to the tails, the blue line is low. So the normal distribution is higher, or Z is higher in the center but lower on the tails. And the T distribution is dependent on sample size. So they've got a couple listed. I think that's the pink one, N equals 1. Which seems weird, a sample size of 1 doesn't seem like a good sample size. And the orange one, which is really hard to see the difference, is the little lower one. That can't be right. It's missing some numbers. Ah, yeah, 15, there we go, that makes more sense. Okay, let me so the N equals 5 is this lower one. And then as N gets larger, as the sample size gets larger, T gets taller in the middle. And lower on the ends until when N gets large enough, T is basically indistinguishable from the normal distribution. I'm gonna undo and shift back over to right, and that should out. So how it differs? D, it's dependent on sample size. But as N gets larger. The standard deviation of the sample. Approaches the standard deviation of the population. And the graphs look and Z T look almost identical. And Z is taller near the center than T. But T is taller in the tails. And this is a property of the standard deviation being greater than the population deviation for most sample sizes. So it takes longer to have the, remember standard deviation is our spread or our dispersion. It's how long it takes for like the heap of sand to spread out. It takes longer to spread out. Or if it spreads out more. You're right, you guys are fast. Alright, so what does that mean? Just like we talked about in chapter 8. If n is greater than 30. This is approximately bell shaped. And following a normal distribution. If n is less than 30, we got some stuff to make sure this happens. We want to check the QQ plot on StatCrunch. It needs to be approximately linear. And how do we check that? This is where we compare R to the critical value. We did this back in chapter 4/7.3. And this happened if the absolute value of R was greater than critical value. We have one more criteria if n is less than 30. The box plot needs to have no outliers. If it does. If either of those is broken, we may not have something that follows a normal distribution. Just like we had Z alpha and alpha represented area to the right. Where without it, it needs to the left. T is the same way. T alpha is area to the right. Where they have a little subscript on it. They don't have the subscript on it, it means it's going to the left. Or less than. Now T had a shitty equation that we don't want to calculate it. T was x bar minus mu over S divided by square root n. We don't want to do that. So what we can do is we can go stats, calculators, T. And all you need to do that is have the degrees of freedom. Given as df. And we've talked about those before, that's n minus 1. I don't know that a lot of problems ask you for the t value. And how are we gonna get the confidence intervals? We're almost to the stack crunch part, and we'll do some examples and we'll be done. To find the confidence intervals. In stack crunch. We're gonna go stats and then T stats. And then we can do one sample. Two sample. Or paired. Now. These three. These have matching hypothesis tests. And we start the hypothesis test on Thursday, yay! Yay, the good shit. This one is in chapter 10. In fact, chapter 10 is all of our single sample ones. Chapter 11 has our two sample ones and our paired. And when we have more than two samples, we have other tests that are not under the T stats. I know the syllabus says 9.3, but we don't have a 9.3 anymore. It used to be telling me the difference between them, but since I do the homework all as one, it's not really in there. Oh, I have a chat comment. Wow, Alfredo, you didn't have to be happy that we'll be done early. I assume that's what the yay is for. How rude. You don't like hearing my voice, Alfredo? Your wife isn't listening to the sweet, sweet tones of my charm. And going, I'm gonna make that handsome guy some oh, you're excited about. That is such a good answer. He says, I'm excited about hypothesis test. I can't wait. Yeah, he might be sincere. That might have been what the yay was for. I didn't look over to see when he said it. All I do know is I said we'll be done in a little while after doing some examples, so I'll believe that. I'll take it. I'll take it. I think you're gonna like hypothesis testing. 80, okay, so the final, there are 10 questions, 2 of them are confidence intervals that are worth 6% each, so 12%. There are 8 hypothesis tests, 11% each. Almost, it is 88% of your final. But they all follow the exact same fucking template. You do this, there's 4 steps, 4 or 5 steps, you do these in order. And the only thing that's different is a single step on every single test. It's the same step that's different in every single step, and it corresponds with what we're looking for. But the rest of it, the way we do it, flushes out, so you only have to really learn one pattern and know what's different. It's good stuff. All right. Let's come over here and look at an assignment. Let's see, this starts section 9. We answered those, you can, and that was part of the stuff we just did. That is proportion stuff. Oh, point estimate. So the point estimate is halfway between the two values. This, you learned how to do it in 9.1 if you watch the video. That would be 21. Which is halfway between 19 and 23. I'm gonna go down and find ones that are more related to what we got here. Here we go. A simple random sample of size n is drawn from a population that is normally distributed. The sample mean x is found to be 109, and sample standard deviation s is found to be 10. Construct a 90% confidence interval about mu if the sample size n is 21. So I am gonna load StatCrunch. And we're gonna go stats. T-stats. One, I guess I need to make it wider. Stats, T-stats, one sample, we have summary information. And now I can shrink this back down. What did they tell us? They told us the sample mean is 109. They said the standard deviation from the sample is 10. And the sample size is 21. And to do a confidence interval, you come down here and click confidence interval. And whatever percentage they want, you do it as a decimal. So they want 95%, we're gonna change this to a 90. This confidence interval proportion or confidence interval is gonna look the same on proportion one. If you haven't done it yet, just the tops changes. And I will click compute. And it's giving me a lower limit and upper limit that corresponds to lower bound and upper bound. And it says round to one decimal place. I have. Let's do that. I have NF, there we go. 105.2 and 112.8. Then it says do a 90% confidence interval amount about mu if the sample size n is 11. I want to keep these results here, so I'm gonna like do this table again. I'm gonna go stats, T-stats, one sample, and with summary was the second one, you can't see it there. This was 109, 10, but now we're doing 11. Confidence interval is 90. And now we've got 103.5 to 114.5. Missing bars in my way. There we go. Check answer. Fantastic. And now it says as the sample size decreases, the margin of error does what? So let me draw here. Let me choose something that'll pop. Red will pop. So when I did, let me do a little curve here. When I had n equals 21. Remember, it's doing a little, well, that's pretty good for using a mouse. Our 90% thing had 105.2 to 112.8. That was for n equals 21. And then along came n equals 11. And we did it, and we had 103.5, which is further to the left, so n equals 11 will be in purple right now. 103.5. And 114.5 is further to the right. Now, mu is in the center. And this distance here is the margin of error E. So it looks like as the sample size went down, as we went from red to purple, I didn't even draw the purple one. Let's draw the purple one. It should be a little bit lower, but go out a little bit further over here. There we go. God, that's a shitty. You deal with it. It's taller on the tails for lower values of n. It looks like as n went down, the error got bigger, the red to the purple. Okay. The margin of error got bigger, so it increased. Now they want us to do, and you can't see that well because I've got text in the way. N is 21, but do 80%. So we had 109. We had 10, back up to 21, but now we want only 80%. And we're gonna probably compare it to the 90% one that had the same value. So this has a 106.1. Up to a 111.9. So doing the stack crunch part is pretty easy. You just plug in values and now they're wanting us to actually try to learn something while we're doing the homework. As the level of confidence decreased, that's what happened, and we went from 90% to 80% with the same sample size. What happened to the size of the interval? Let's take a look at that. Let's do blue for this picture. So 106.1 is closer. Like 106.1 is inward sum. And 111.9 is less than 112. So 111.9 is right about there. Which means our error, rather than making this long greeny here, is only going out that far this time. So our error looks like it's gotten smaller. By decreasing our confidence level, the error has decreased as well, or the size of the interval has decreased as well. So that's important to know. What will adjust the confidence intervals and stuff like that. When you do the problem, you'll hopefully you're not doing it right now. When you do the problem, you'll go through this as well. Think back to doing like making a little chart and figuring out what's going on. Then it asks, let me clear the annotations. Could we have computed the confidence interval if the population had not been normally distributed? Well, our sample size was below 30. So it didn't default to being normally distributed. Which means no. The population needs to be normally distributed because the sample sizes are less than 10 or less than 30. Which is D. You want greater than 30, or you need to know that it's normally distributed. Which means the way I wrote this earlier is probably not the best way. Let me come back over here and change what I wrote on the. I said if n is greater than or equal to 30, it is bell-shaped. But also, the other thing is or normally distributed as stated. If they tell us it's normally distributed, we don't need to worry about shit. That's the ideal one, when they just tell you it's normally distributed, you don't even have to put any thought into it. That makes sense, so kind of like how it works and what you're doing? You guys have any questions? Would you like to leave, or would you like to work on homework here, or would you like me to tell you to get the fuck out? Or would you like to go on? Vote? How could, wait, what did you say? How can any go and stay?
No, get the fuck out and go.
Oh, yeah, okay, let's wrap it up. On Thursday, we will start hypothesis testing, we're gonna do a little experiment in class, it'll be fun. I promise you, it'll be fun, I'm not the only one that'll enjoy it though, sometimes when I say it's fun, it's not sometimes it's only fun for me. I think you guys will have fun. We will start talking about the project after we've started talking about hypothesis testing. You can't do the project until you start having hypothesis tests. And do I have it on the syllabus? Let me go look. We will talk about the project next Tuesday. On the 29th. That's what we'll introduce the madness that begins. Okay. Yeah. Brooklyn was asking on Zoom.
Alright, see you Thursday.
See you guys.